In section 5.1, we're going to be introduced to two new quantities, momentum and impulse. These terms might exist in your vocabulary, and I want to see if the definition, as you have been using them, how it compares to the physical definition or the definition in physics. Let's start with momentum. Linear momentum is given the symbol lowercase p with an arrowhead on top. This indicates that this is a vector quantity. It's defined as a quantity that describes the motion of an object traveling in a straight line as a product of both its mass and its velocity. The equation for momentum is mass times velocity. So we can deduce that the unit for momentum is kilograms times meters per second. Note that for the rest of this section, the term momentum refers to linear momentum. The momentum of an object is directly proportional to the object's velocity. So the vector is along the same direction as the velocity. Note also that momentum is proportional to the mass of the object. Let's try a sample problem. Calculate the momentum of a 2.5 kilogram rabbit traveling with a velocity of 2 meters per second east. Then calculate the momentum of a 5 kilogram groundhog traveling with a velocity of 1 meter per second south. Let's start with the rabbit. We have a mass of 2.5 kilograms and a velocity of 2 meters per second east. If we punch this in, we end up with 5.0 kilograms times meters per second east. Let's do the same for the groundhog. Here we have 5 kilograms with a reduced speed of 1 meter per second south. Multiplying in our calculator, we get 5 kilograms times meters per second south. If we compare the magnitude of the momentum for the rabbit and the groundhog, we see that they both have the same magnitude. It's 5 kilograms times meters per second. Even though the mass is different for each and the speed or velocity is different for each, we end up with the same momentum. Now let's compare momentum and kinetic energies for these two organisms. Let's find the kinetic energy of the rabbit. Note, we do not need to put in the direction for the speed in this example because kinetic energy is a scalar quantity. If we compute this in our calculator, we end up with 5 joules of kinetic energy. Let's see how this compares to the kinetic energy of the groundhog. Punching this into our calculator, we see that we have 2.5 joules of kinetic energy for the groundhog. So even though their momentums were the same, they have different kinetic energies. There are two variables, the mass and the speed, that are used in both momentum and kinetic energy. In kinetic energy, the speed that the object possesses plays a larger role. It's exponentially related to the kinetic energy. So as a result, we see that the rabbit has a greater kinetic energy than the groundhog. The second term is impulse. Let's start with an example. A golf ball resting on a tee has mass but zero velocity. Its momentum, therefore, is zero. Although the golfer may not think of it in these terms, the goal is to use that golf club to change the momentum of the ball. If the golfer is successful, the golf ball will fly through the air with considerable momentum an instant after colliding with the club. So what happens during this transition? Well, Newton's first law states that the velocity of an object is constant unless acted on by an external force. So in the absence of an external force, an object with constant mass must also have constant linear momentum. If a net force is applied to the object, its velocity will change, and therefore its momentum will also change. Below we can see how Newton's second law can be used to calculate the formula for impulse. Let's define impulse. Impulse is defined as the product of the force and time that acts on an object to produce a change. The equation for impulse is F delta t. And F delta t is equal to the change in momentum that the object receives. So if you apply a force on an object over a given amount of time, you will change the momentum of the object. Let's try a sample problem. A 0.160 kilogram puck is traveling at 5 meters per second north. A slap shot produces a collision that lasts for 0.0020 seconds and gives the puck a velocity of 40.0 meters per second south. In part A, they ask us to calculate the impulse imparted by the hockey stick. If we know the change in momentum of the hockey stick causing onto this hockey puck, we will be able to calculate the impulse that was delivered. So let's try this. The change in momentum is mv2 minus mv1. We can factor this out. Not necessary, but it makes it a little cleaner. So it's m times v2 minus v1. If we sub and solve, we have 0.160 kilograms times 40 meters per second south minus 5.0 meters per second north. Knowing that these are vector quantities, we have to make sure that we make both of the directions the same. When doing so, we change the sign of the vector. So the second step is 0.160 kilograms times 40 meters per second south plus 5 meters per second south. Compute this in our calculator, and we end up with a change in momentum of 7.2 kilograms times meters per second south. We can also express this in the units that are best represented for impulse. Since impulse is force times time, 7.2 kilograms times meters per second can be converted to Newton seconds. Therefore, the impulse or change in momentum imparted by the hockey stick is 7.2 Newton seconds south. In part B, we want to determine the average force applied by the stick to the puck. We know the change in impulse is equal to the force times time. So rearranging for this force, we can calculate it by dividing the change in impulse by the time which this force was in contact with the hockey puck. So we have 7.2 Newton seconds south divided by 0.0020 seconds. If we punch this into our calculator, we get 3,600 newtons south. Therefore, the average force applied by the stick to the puck is 3.6 times 10 to the power of 3 newtons south. Very good. Let's try an additional sample problem. This sample problem reads, a volleyball player starts a serve by throwing the ball vertically upward. The 260-gram volleyball comes to rest at its maximum height. This is the moment in which the server hits the ball and exerts an average horizontal force of magnitude 6.5 newtons on the ball. Determine the speed of the ball after the player hits it if the average force exerted on the ball is exerted for 615 milliseconds. So we know that the impulse is equal to the change in momentum. We know that the impulse, therefore, is equal to mv2 minus v1. We can rearrange this equation for v2. If we do so, divide both sides by m, we end up with v2 is equal to f delta t over m plus v1. Now we know that the moment at which this volleyball is struck, that it was at rest. That was mentioned. So this term right here is going to be equal to 0. So v2 is equal to f delta t divided by mass. We know the force is 6.5 newtons. We know the time of impact is 0.615 seconds. Just an aside, 615 milliseconds is equal to 0.615 seconds. And I got that by dividing by 1,000. Divide this by the mass, 260 grams or 0.260 kilograms. We end up with a final speed of 15 meters per second. Therefore, the speed of the volleyball when the force is exerted for 615 milliseconds is 15 meters per second. In part B, we have the same initial conditions. The volleyball player throws the ball up in the air. The moment it's at rest in the air, strikes the ball with the same horizontal force, but this time the time interval is 875 milliseconds. So we want to see how this impacts the speed of the volleyball. The equation will be the same. Force is the same. Now we're dealing with 0.875 seconds. And the mass again is 0.260 kilograms. If we punch this into our calculator, we end up with a greater speed, 22 meters per second. And this makes sense. The second situation, the volleyball was in contact with the force for a greater amount of time, therefore resulting in a larger speed. If you're a volleyball player, note that by following through on your serve, you will increase the time interval for the applied force, resulting in a faster serve. So please follow through on your serve. In sample problem number 3, we're going to look at the area underneath a force versus time graph. Impulse is equal to the area under a force-time curve. So here we have a situation in which two figure skaters approach each other in a straight line. They meet hand to hand and then push off in opposite directions. The increase and decrease of the force are both linear, which produces a force-time curve that is in the shape of a triangle. Force-time curve for this interaction is shown below. Let's determine the impulse for this interaction. So the impulse is equal to the area under the force-time curve. In this case, It's a triangle. The area of a triangle is base times height divided by 2. The base of this triangle is 2.5 seconds. The height is 20.0 newtons. I want to include the direction. Divide this by 2. Computing this, we end up with an impulse of 25 Newton seconds. Therefore, the impulse of the interaction of the two skaters is 25 Newton seconds away from each other. Please review these concepts and practice them with the homework below.